Namaskar, a very good morning or afternoon, wherever you are to one and all for attending this 35th PRL का Amrut Vyakhyaan. On behalf of PRL, I, D. Pallamraju, welcome all of you who are joining us through the WebEx platform and the PRL's YouTube channel. PRL came into existence in the year 1947. So, along with the nation's 75th year of celebrations of Azadi Ka Amrut Mahotsav, PRL is celebrating its Platinum Jubilee year. And as part of the Platinum Jubilee celebrations, PRL has initiated several exciting programs and events. And one among them is this lecture series, which is called the PRL Ka Amrut Vyakhyaan, wherein we invite people of eminence in the fields of science, engineering, technology, arts, literature, business, and law to share with us their excitement, and so that we can enhance our knowledge. There will be 75 such Vyakhyans in this series. This started on the 4th of August last year and will be going on until the early next year. All the lectures delivered so far are available on PRL's YouTube channel, and I encourage all of you to view these exciting and excellent lectures. I take this opportunity to also request all of you to please stay tuned on all the Wednesdays for the forthcoming lectures as well. Today, the 35th PRL Ka Amrut Vyakhyaan will be delivered by Professor Subir Sachdev, who is Herschel Professor of Physics at Harvard University, Cambridge. He will be speaking on an exciting topic, quantum entanglement at all distances. On behalf of PRL, I would like to thank Professor Subir Sachdev for kindly accepting our invitation and agreeing to deliver this Vyakhyaan. To formally introduce Professor Sachdev to this audience, I will invite my colleague, Professor Janardhan. Professor Janardhan, please go ahead.
Well, thank you, Professor Pallamraju, and a very good afternoon to everybody in this Platinum Jubilee year of PRL. As Sir Raju has already said, we will be through a series of 75 lectures by very eminent researchers and personalities who have contributed to nation building, be honoring the memory of Vikram Sarabhai, who not only founded PRL, but whose vision led to the formation of the Indian Space Research Organization, ISRO, which has given India a preeminent place in the world for the use of space for human development. On an occasion such as this, it is a great privilege and honor for me to introduce to this audience my classmate from St. Joseph's European Boys High School, Bangalore, my friend of nearly 5 decades, and now a world-renowned condensed matter theorist, today's speaker, Professor Subir Sachdev. Professor Sachdev has had an enviable academic record, and I dare say that he has never experienced what it is to come second in any academic course. After his freshman year at IIT Delhi, he moved to the USA and obtained his PhD in theoretical physics from Harvard University in 1985. Since 2015, he has been the Herschel Smith Professor of Physics at Harvard, and he is currently serving as the Maureen and John Hendricks Distinguished Visiting Professor at the Institute of Advanced Study at Princeton. Professor Sachdev is well known globally for his many seminal contributions to the theory of strongly interacting condensed matter systems. He is a pioneer in the study of systems near quantum phase transitions, and he has explored the rich variety of static and dynamic behavior in such systems, both at finite temperatures and at T equal to 0. He has published 2 books, the first of which, entitled Quantum Phase Transitions, published by Cambridge University Press in 1999, has now become the basic text in the field, and it has over 8,400 citations. He has also pioneered the exploration of the connection between the physical properties of modern quantum materials and the nature of quantum entanglement in their many-particle state, thereby elucidating the diverse varieties of entangled states of quantum matter. Professor Sachdev has received many honors and recognitions, and I will list those that he has received in, say, the past 10 years, because listing them all will take a great deal of time. He is an elected member of the American Academy of Arts and Science, 2019. He is an honorary fellow of the Indian Academy of Sciences, Bengaluru, 2019. He is an elected foreign fellow of the Indian National Science Academy, 2019. He has been awarded the Dirac Medal by the International Center for Theoretical Physics at Trieste, 2018. And he has been awarded the Lars Onsager Prize from the American Physical Society, 2018. Between 2016 and 2019, he held the Dr. Homi Bhabha Chair Professorship at the Tata Institute of Fundamental Research, Mumbai. He has been elected to the US National Academy of Sciences in April 2014. Professor Sachdev has published over 700 research papers in his career so far, which, believe it or not, collectively have citations of over 54,000 and a H index of 114. He has produced over 30 PhDs and has mentored over 50 postdoctoral fellows. Before handing over the floor to Professor Sachdev, let me thank him once again for agreeing to give this talk at what must be a very early morning hour for him on the East Coast. And also say that the title of your talk today, Professor Sachdev, Quantum Entanglement at All Distances, has created a lot of excitement here, as some of my colleagues at PRL are actively involved in experimenting with several entanglement-based protocols for quantum key distribution over distances of up to 3,300 meters through the atmosphere. So with this, I invite you, Professor Sachdev, to deliver your talk. Thank you very much.
Well, so can you hear me?
Yes.
All right. Okay. So thank you very much, Professor Palamraju and Professor Janardhan and Professor Srivastava for this kind invitation. It's certainly an honor for me to make this long distance presentation at PRL. I visited PRL a few years ago, and it was a pleasure to meet some of you at that time. And I hope there'll be another occasion in the future. All right, so, and thank you for that kind introduction, Jerry. There was just one small error. I have not published 700 papers. I think it's smaller than that. Okay, that would be impossible.
Google Scholar
Okay.
reports close to that number.
Oh, is that right? Okay. Well, okay. Thank you anyway. Well, yeah. All right. So yes, I do remember my school days with Professor Janardhan, and you know, and it's really wonderful to share the memories from those time and to see you again. Okay, so let me now share the screen. Okay, so I hope you can see it and also see, hear me and see the red pointer.
Yes.
Okay, so all right, so I'm going to talk about the role of quantum entanglement in a couple of different fields of physics. This talk is, designed for people who have a little bit of physics knowledge, science undergraduates and graduate students, but I hope the rest of you who don't have a physics degree can also follow along, and maybe you can ask me questions later on. There'll be a few slides where I'll get a little technical, but most of it is fairly broad. Okay, so one field of physics where quantum entanglement plays a fundamental role is in the theory of metals. And I'll begin this by describing what we call ordinary metals today and what we call strange metals. It'll of course be in strange metals where quantum entanglement will rear its head. Okay, oops, what's going on? All right, so if I take an ordinary metal like copper, so it's made up of a lattice of copper atoms. And what happens in the metallic state is that the outermost electron of a copper atom gets delocalized, and these electrons move through the entire crystal. And that's how electrical current and heat flow through a copper wire. Now, these electrons, as they're moving around, also repel each other. And so by the Coulomb's law. And so this can modify the motion of these electrons. But it turns out that for most purposes, you can ignore that interaction and treat the flow of current as just the flow of individual particles. So there's still the problem of how do you describe the collective flow of so many particles through a wire. And the theory of that really goes back to now 2 centuries ago to the fundamental contributions of Boltzmann. So Boltzmann was working in the 19th century before even the invention of quantum mechanics. And the problem he was addressing was, the classical gas in the atmosphere, oxygen or nitrogen, and how we describe the motion of these molecules obeying Newton's laws, and how that leads to equations of state like PV equals nRT, and various other thermodynamic properties. So he made 2 fundamental contributions, both of which I'm going to use in a key way today. One is the statistical understanding of entropy, that the entropy, which previously had been viewed as a thermodynamic property that came about from study of heat engines and the second law of thermodynamics, he gave it a microscopic statistical interpretation. And his famous formula, S equals K log W, is on his gravestone right here. So what this relates is the entropy S to W, where W, roughly speaking, is the number of microstates available to the molecules in a gas for a given macrostate. So it has a certain temperature and a pressure, but there are many different microstates consistent with that temperature and pressure and volume. And some estimate, taking the log of that, gives you an entropy, which is extensive, meaning it's proportional to the volume of the gas. Now, this particular interpretation actually survived the development of quantum mechanics in the earlier 20th century. And quantum mechanics tells us that the energies of any system are quantized into discrete energy levels. And so then you can look at what's called the density of states, which is the number of energy levels in some small energy window. And you just take, so this density of states plays the role of W. And so if you exponentiate this, you have the density of states is the exponential of the entropy. So this is the modern definition of what entropy is. Okay. The other important contribution of Boltzmann is the Boltzmann equation. So I apologize for the equation that I'm throwing at you. I won't really use it, just to show you the famous Boltzmann equation for once. So what the Boltzmann equation describes is the collision of these molecules. After all, the molecules have to collide with each other to come to thermodynamic equilibrium. But these collisions are very rare. And that was the assumption that Boltzmann used. And he further used the assumption that once one collision happens, say these 2 molecules collide with these momenta to give this output, then the subsequent collisions, there'll be more collisions afterwards, are statistically independent. So you don't have to worry about the fact that these 2 molecules here had just collided with had collided with each other. So you can just treat them as just any other pair of molecules. So using the statistical independence and the diluteness of the gas, which leads to rare collisions, he derived this equation. So the left-hand side of the equation is expressed in terms of the basic quantity Fp, which is basically the number of molecules momentum P. And the left-hand side is a complicated way of writing down Newton's laws. And the right-hand side is the collision term. That was his famous innovation. And the collision term conserves energy. That's what this term says, and it conserves momentum. And there's a certain probability that the collision occurs, and that's t squared. Okay, so from this famous equation, it's amazing, just about every property of a classical gas can be understood. How it flows, its viscosity, how it behaves with temperature, and so on. It became really the very foundation of our study of any gas. But the amazing thing is this equation that Boltzmann invented for a classical gas in a room also applies to these electrons moving in a copper wire. So can we apply the Boltzmann equation to these electrons? And the answer is you can, somewhat surprisingly, but with one change. So now these electrons in a wire are not dilute in any sense of the word. There's one electron for every atom. So they're really very dense. So you would think that you couldn't possibly apply the Boltzmann equation. And the other problem is that they're not classical. They obey the laws of quantum mechanics. They have a wave-like nature. And so that also Boltzmann didn't take into account. But somehow, amazingly, these two new features kind of cancel each other. So here's the classical Boltzmann equation, and here's the quantum Boltzmann equation. The only change, if you look carefully, is what happened here in the collision term. So in the collision term, I had the product of two Fs. This is just the probability that I have two particle at momentum P and particle at momentum P1, and then they collide with each other. And the other term is for the reverse process, which can also happen. So that's quite simple to understand. And now this F term, if in the quantum theory, becomes F times 1 minus F times 1 minus F. And that's where you put in the quantum mechanics or the exclusion principle. So this is telling you these two can collide and scatter into the state on the right, but they can only go there if the state was empty to begin with. So that's the 1 minus F. So that's the quantum mechanics, 1 minus F. And the magic is this 1 minus F makes the collision much rarer. So even though the gas is dense, Pauli's exclusion principle makes collisions very rare. And that also means any kind of quantum interference, which is another word for entanglement today, between successive collisions can be ignored. All right, so it was Landau mostly in the Soviet Union in the 50s who pointed out that the Boltzmann equation still had some life left in it and could be applied to electrons in a metal. And this quantum Boltzmann equation, that's often called, is really essentially the theory for transport of current in metals. So you can solve that equation and you get various properties that metals display, metals like copper. For example, you find that as you lower the temperature, the collisions become rarer and rarer. And as temperature goes to 0, the collision time, the time between collisions, diverges 1 over temperature squared. And one of the consequences, the resistivity of a metal at low temperatures has a t squared correction, and that's the same t squared here. And because as the resistance, most scattering events happen more often, the resistance goes up. Okay, so now you can ask, okay, that's really amazing that you can apply the Boltzmann equation with independent successive collisions. When does it break down? Well, Landau came up with this in the 50s, and for, I would say, about 40 years, this worked beautifully. It is really the basis of almost everything in solid state physics. All of semiconductors, the whole semiconductor technology really uses these ideas in a fundamental way. Okay. So, but as theorists, we want to keep pushing the envelope and keep asking, when does this going to break down? How often, why is it just so amazingly successful? So you have to ask, when, or another way to ask this question is how often do collisions have to happen for this approach not to work? So you can ask, how short can you make the collision time? Well, there's kind of a quantum uncertainty principle that comes up, which I proposed many, many years ago, that the limiting time is now what's called the Planckian time. So using Planck's constant h bar and the value of temperature, Boltzmann's constant kb is a fake constant. It's just needed because we insist on measuring temperature in degrees centigrade or degrees Kelvin, rather than in units of energy. So if you divide Planck's constant by energy, you get a time. And this is some sort of an energy time uncertainty principle. Since the typical energy of an electron is kBt, that means you can't even define the electron if the collision time becomes shorter than h bar over energy. So, so as long as this time t is longer than this time, then you can apply the Boltzmann equation and use the independent particle picture with rare collisions, rare statistically independent collisions. And so as you see, as temperature goes to 0, since it blows up as t squared, and this blows up as 1 over t, this is always longer than this, and everything is all okay. So the rough idea is that these electrons, even though dense, keep moving along merrily, and ballistically, as we sometimes say, and then they collide. And after, if you look at longer times than the collision time, then you get chaotic behavior, much like the chaotic behavior of molecules in a classical gas. All right, so that's a quick summary of about 100 years of work and how it led to a very successful theory of motions of electrons in insulators, metals, semiconductors, and even superconductors with a few changes. All right, so then why am I talking about this till today? So really the big impetus for going beyond Boltzmann came at the discovery of these materials, yttrium, barium, copper oxide, in 1987 by Bednarz and Mueller. They actually didn't discover this particular material, but a closely one. And the great excitement was that these materials in room, in ambient pressure, can have a critical temperature of around 100 Kelvin and even above. And this is above the boiling point of liquid nitrogen, so it's very easy to do a lecture demonstration, which I've done many times, where you take a little crystal of this and put it in liquid nitrogen, and then you find that it can conduct electricity without resistance and also float in a magnetic field. And these days, these materials are being used in the next generation of fusion machine to create high magnetic fields. All right, well, I could give a whole lecture about superconductivity, but that's not what I'm going to talk about. What there's been also a lot of interest is in what happens right here when you raise the temperature above the superconducting temperature. And the reason you want to understand this state here is because, well, it's this state, of course, as the parent of the superconductor. So once you understand this state on a microscopic basis, maybe you'll have a better understanding of why the critical temperature is so high in these materials, much higher than any previous material. And even today, in ambient pressure, this is the highest. These class of materials have the highest critical temperatures. So this particular regime here, the first guess should be just like copper. Because other superconductors like aluminum and copper, aluminum certainly, and lead, behave like copper once you raise the temperature above the superconducting TC. But they don't, and this regime is called the strange metal. And this, we wish we had a better word, but that's what we call it. And it's strange because it doesn't look like copper. And when you investigate its properties, they're really remarkably different. So I'll just show you a couple of, it's been studied a lot in the past 30 years. I'll just show you just a couple of experiments. So very recent ones. So here's an experiment by the groups of Louis Taillefer and Brad Ramshaw, measuring precisely this quantity, the scattering time. I won't go into exactly how they measured it. They have to use high magnetic fields and look at the flow of current in different directions. And from that measurement, they can read off a time that they call tau iso. This is the isotropic component of it as a function of angle. And if you look at the value of tau iso, which is that red dashed line, it's actually exactly the Planckian time. So tau is h bar over kt, which is precisely the limit for the breakdown. If it became any shorter, you would have a complete breakdown of the Boltzmann approach. So it's right at the margins, and in fact, there's a fundamental argument that it can't go any below. So this means that we can't use Boltzmann equation. The electrons here are not really independent. We call these quasi-independent electrons quasi-particles. There are no quasi-particles present, and really have to come up with a whole different way of thinking about electron flow in this material. So these electrons, since they're not independent, are entangled with each other. And I'll say a little bit more about entangled and what entanglement is in a few minutes. Another set of experiments let me show you is the temperature dependence of the resistivity, which I recall I said had to go at T squared. But you see, this is one of the high temperature superconductors. It's linear in temperature over a wide temperature range, really down. This is the superconducting transition, but if you apply a magnetic field, you can see the linearity go to even lower temperatures. This really is it's been a long-standing mystery. I won't say it's a complete mystery because we think we have made some progress in understanding this, which I'll discuss a little bit towards the end of my talk. This is a measurement in a completely different set of materials, magic angle trilayer graphene, bilayer graphene, a new set of materials just discovered a few years ago. Very different microscopic system, but again, they have superconductivity, and above the critical temperature, you again see a beautiful linearity behavior. So if there's any explanation for this linearity, you want it to have some degree of universality. You know, it's not just in the cuprates. You can't use a very specific cuprate model because we see it in a variety of materials, and I've just shown you two of them. All right, so a lot of these observations have, opened some questions, which we think we're starting to understand, but they're really mostly open questions today. So what we really need is a theory. We have a theory of flow of current in copper. We need a theory of flow of current in a strange metal, where the individual electrons lose their identity because they're interacting with each other so often, and you cannot neglect the interference between successive interactions. So there's this, as we say, an entangled soup of electrons. How do you understand its flow and predict its properties? And once you have a theory for this, you want to figure out why is it that the resistivity is giving you this Planckian time behavior. Collision time is very close to h power over kt. And then finally, and this I won't say anything about today because it's mostly an open subject. Once you have a strange metal, why is a strange metal lead to superconductivity at much higher temperature than before? Okay, so that's an introduction to one class of systems where entanglement, it's clear, is starting to play a role. Let me now turn to something completely different, something I certainly didn't know anything about in the 90s, which are black holes. And at least on the theory side, there's now been an appreciation of how quantum entanglement also plays a crucial role to properties of black holes, which are far from being measured, the quantum properties. And in fact, there's a connection between the quantum entanglement of black holes and the quantum entanglement in a strange metal. And that's kind of the main theme of my talk. I'm taking you from quantum entanglement in a little crystal that you can hold in your hand to an astrophysical object. Okay, so first of all, what are black holes? Black holes were discovered by Schwarzschild as a solution of Einstein's theory of general relativity, theoretically. Today, they're observed, and there's a black hole at the center of every galaxy, including our Milky Way, and the LIGO Observatory, which there's going to be one in India, is measuring gravity waves coming off from black holes. But anyway, so a black hole is a very, very dense object. You take an object of mass m, where g is Newton's constant and c is the velocity of light. From this combination, you can create the horizon radius. And if you compress a mass m to a radius smaller than r, it becomes a black hole. And it's an extremely dense object. It's so dense that light itself bends back and is not able to go past the horizon. Okay, so this was a solution of Einstein's equations discovered in the 20s, and nobody took it seriously for a long time until Oppenheimer and Chandrasekhar and others pointed out that there's a reasonable possibility these could actually be around in our universe, and today they're everywhere. Just to get a sense of scale, how dense this is, if you put it in the Earth's mass, this radius r is 9 millimeters. So you would have to compress the entire Earth to a radius of 9 millimeters to get a black hole. But there is such an object at the center of the Milky Way with a mass of, I think, several million times the mass of the sun. So its radius is about the size of the Earth's orbit, I think, around the sun. All right. So what about quantum? Why should I worry about quantum entanglement? So first, let me just remind you what is quantum entanglement. So here's say a molecule of hydrogen. So there's 2 electrons in a molecule of hydrogen, and the electrons have a spin. So one possible state of these 2 electrons is one electron has a spin up and the other electron has a spin down. The other possible state is the opposite assignment. But the actual configuration of these electrons is this superposition of up, down, minus, down, up, and that's an entangled state of the electron. This means that when I separate the 2 electrons far away, and I happen to look at the one on the left, and I see it's up, then because these were entangled in the past, then only at that instant is the other electron collapsed into a state down. So this kind of entanglement has been observed on Earth and also now in satellite experiments, where observation of one electron instantaneously influences the state of the other electron. Actually, I didn't say that quite right. The 2 electrons share a state. So measurement of one can naturally influence the subsequent measurement of the other. It's not as if a state is some information is going from here to there. They shared a state because they were entangled in the past. All right, so now imagine a thought experiment where these 2 electrons are right at the horizon of a black hole. And so one of them falls in and the other one falls out. And you're sitting outside the black hole, fortunately, and you have this electron with you. And there's no possible way for you to ever find out, even if somebody inside the black hole measured the other electron, they can't send you a signal and tell you what they measured. So as far as you're concerned, this electron is on its own, and the other electron is past the horizon, is gone beyond the horizon. So for you, this electron is not entangled with anything. It's just a random electron that can be either up or down. So there's some degree of randomness here that in this electron that you have with you. And randomness is what Boltzmann taught us is what leads to entropy. So therefore, they come with this amazing conclusion that because there can be quantum entanglement, so classically nothing can ever talk to, no influence of the inside can go outside. But quantum mechanically, there can, by this entangled process, if you have an entangled pair fall apart in this way, there's still entanglement. Nothing special happens at the horizon. But sitting outside, you won't be aware of the entanglement, and so you're going to see a random electron. And so, as Boltzmann taught us, this means that there's an entropy. So Hawking and Bekenstein a bit earlier used such arguments, not this argument precisely, to argue that black holes have a quantum temperature and an entropy. And the entanglement reasoning is that to an outside observer, the state of the electron inside the black hole cannot be known, and so the outside electron is in a random state. Okay, so Hawking and Gibbons a bit later Gibbons and Hawking did something much more. They gave us actual expressions for the Hawking temperature and the entropy. And they did this by, one of the ways they did it was by evaluating the Feynman path integral of Einstein gravity in imaginary time using a certain semi-classical approximation. So, so this result, I now know is completely correct. It was really an amazingly brilliant contribution. But if you looked at the computation, it really was, questionable. It had a lot of inspired guesses and unjustified steps, including going to imaginary time and using a semi-classical approximation. And one could be, justified in being skeptical that this was indeed correct. This was not the type of calculation you would do in quantum mechanics when you say work out the structure of a hydrogen atom. You solve the Schrodinger equation completely, you get all the energy levels. There's no energy levels here, nothing. It was just it was an inspired guess, but an amazingly correct and brilliant contribution. All right, so if you believe these results, so here H bar, everything I've explained, what all the numbers are here, yeah. So if you believe these results, you come up with some rather amazing conclusions. First of all, the entropy is finite of a black hole. Now this was quite remarkable because by this time people had been doing theories of quantum electrodynamics, of quantum fluctuation of the electromagnetic field, and that those fluctuations have no short distance cutoff. They can appear at any microscopic scale whatsoever. And so if you did the computation in quantum electrodynamics, because of the very, very short distance quantum fluctuations, you will get an infinite entropy. Somehow, when you go to a black hole and put in gravity, there seems to be a discreteness to space itself. And that's leading to an entropy. Furthermore, unlike, say, the Boltzmann computation of entropy in a classical gas, it's not proportional to the volume. It's proportional to the area. So you have this two remarkable features that come from this calculation of Hawking, which are really hard to stomach. But if you take them seriously, you have this rather crude picture. First of all, there's some discreteness to space-time. So this is, I've drawn a bunch of bits, which are ones and zero, but these are quantum bits. So there's some discreteness to them, and the black hole is somehow described by a bunch of quantum bits at some microscopic scale, some very short scale. And secondly, the number of bits don't fill the volume of the black hole, they're on the surface. So that's what this picture is supposed to be. Don't take it too literally, that's supposed to represent what's going on here. All right, so this is back in '74, and these conclusions were so remarkable that people were justifiably skeptical. There was a further conclusion that the black holes also start to evaporate because it's like a black body at a certain temperature, so it's always giving off some radiation. And then there became questions of exactly how these discrete quantum bits, all the information in these bits is coming out in the radiation. And Hawking argued that, in fact, there seemed to be no information coming out in the radiation. It was purely thermal, just like a black body. And so this led to various information paradoxes. And even, I think, for a while, Hawking asserted that this must mean there's something wrong with quantum mechanics at this microscopic scale, and we need a new theory. Okay, so on that point, Hawking was not correct. I think probably admitted it at some point in his life. But he was correct about everything else. So it turns out you can understand all of these properties using the conventional quantum mechanics. Nothing is needed to modify the conventional quantum theory, which I'll say a little bit about as I go along. All right. So another interesting property of black holes was worked out by Vyakhyaan first. which he asked the question, what happens when you perturb the black hole a little bit? Say another star falls into it, and that perturbs the black hole, and it starts to oscillate a little bit, and then eventually come to rest. You can ask, how long does it take? So Visvesvara computed this, and the time was 8 pi GMC cubed. Now, so this was before Hawking's paper, as you can see. But now if you take Visvesvara's result, which has no H bar in it, and express it in terms of the Hawking temperature, then you find it's exactly this Planckian time. So this is the first hint, and it was actually the first hint to me personally, that there's a connection between a strange metal and a black hole, because they both have the same relaxation time, or collision time. In the case of a strange metal, here is the relaxation time to thermal equilibrium, which is h bar divided by the temperature, in which case you have to put Hawking's temperature here. Okay, so here I show you some experimental data actually from LIGO measurements where people have measured the relaxation time of these on the merger of two black holes, and they also, and from the data you do find that this time is peaked very closely to h bar over kt. I mean, this is not a surprise, and this is not a quantum effect because it's just the Visvesvara time. There's an h bar here and the h bar here, and they cancel each other. But it's curious so the point here is that there's two ways of thinking about a black hole. You can think about it using the Einstein equation, and this is the answer you would get, 8 pi gm over c cubed. Or you can think of it as a bunch of qubits which are coming to thermal equilibrium. And if you take that point of view, you get the Planckian time. And these two must be equivalent, and that's the principle behind, in a way, what's called holography, the connection between these qubits on the surface and Einstein gravity. Okay, so this, as I've already mentioned, raises a lot of questions, which have been the focus of a lot of work since Hawking's brilliant contributions. And I think today there's an emerging understanding to some of these questions. So the questions being, Hawking's calculation was just kind of semi-classical. It didn't use the full Schrodinger equation, which gave discrete state. It seemed to not even worry about the discreteness of states. So can you get the Hawking answer in a model that has discrete quantum states? And once you have that answer, can you compute corrections to this thing? And in fact, this kind of computation would require this holography. So that is, can you use this picture of qubits to give you both the theory of gravity and also understand the Hawking entropy? So by unitary quantum system, I mean these qubits sitting on the surface, and they're in one lower spatial dimension because they're on the surface and not the volume. And once you have a theory of these qubits, will you find, as Einstein's equation predict, that they relax to equilibrium in this Planckian time, h bar over temperature? And can you understand how the entropy of the black hole, how the information and all the state of a black hole, how that information goes into the radiation? Can the radiation be described using the same holographic description? Okay, now we don't have answers to these questions today. I'm sure if there are some string theorists, other gravitational physicists in the audience, they will challenge me. But in some simpler context, some simpler sort of black holes, I think it's fair to say this understanding has moved. We have beginnings of answer to all of these questions, and I'll try to give you some inkling of that. Okay, so I've spent, how am I doing on time? I have not that much time. I'm about 15 minutes or 20 minutes, something like that. Is that correct?
Yes, 10 to 15 minutes, yes.
Okay. All right, so let me now, I've given you, described two different fields of physics and shown you how experiments in theory in these two fields lead to a lot of open questions. One is the theory of strange metals in say the cuprate superconductors and other materials, and the other is the entropy and the quantumic theory of a black hole. And there's a connection between these two problems. The main connection being so far this kVt over h bar common time. Okay, but the connection in some cases can be made much more precise, and this relies on this model that's called the Syk model. So what is the Syk model? Well, I'll show you what it is. So this was something, a variant of it that I came up with in 1993 when I was thinking about the strange metals. And basically, my idea was, well, this problem is too difficult. I just want any model, no matter how ridiculous, unrealistic, shall we say, which at least can show you how you can get the loss of quasi-particles. That is, you can account for the, where the Boltzmann equation breaks down. You can account for quantum interference between successive collisions, and leading to some metallic state which has no particle-like excitations. So once we have a model, maybe then we start to understand how quantum entanglement can spread to a big system. The underlying picture of Boltzmann was that, or Boltzmann and Lambda, was that it didn't spread. It just, there was a collision, and that's really all about. That's the only time you have to worry about quantum mechanics. All right, so we have to start thinking about quantum entanglement for more than 2 electrons at a time. That's really the key. I only talked about pair of electrons. You have to think about a whole black hole worth of electrons. So again, ideas on how you have entanglement in more than 2 electrons go back to the 19th century. In this case, this is August Kekulé, was a chemist, again, before the invention of quantum mechanics, where he proposed a theory of the benzene molecule. So a benzene molecule, here's the structure of benzene. Let me just focus on just a single electron on the carbon atom. So it forms this covalent bond. This double line indicates that extra bond between this last electron. So these 2 carbon atoms form a covalent bond, meaning they are entangled. These 2 electrons are entangled, and these 2 electrons are entangled. But no, there's another choice where these 2 could be entangled, this 2 could be entangled, and these 2 could be entangled. And the actual result, and this is what Kekulé proposed, was well, he didn't use the word superposition. He said they resonated between these 2 configurations. They were hopping back and forth between these 2 configurations. So in the modern quantum theory would say you now have an entangled state of 6 electrons, which is this resonating of the valence bonds between this state and the other state. And in fact, he said that he had this idea in a daydream of a snake seizing its own tail. Well, now we want to take the idea of Kekulé and resonating valence bonds to an infinite number of electrons. So I can say it's sort of like this game of snakes and ladders. Rather than a snake seizing its own tail, these snakes, which represent entanglement, can entangle any point with any other point. And that, in a nutshell, is what is the Syk model. So here's a specific description. You take a bunch of sites where electrons could reside. And these are the electrons, the purple dots. And so this is one possible state of the electrons, just like one possible state of a benzene molecule. And now they're going to entangle with each other. And so you have to give some rule or some Hamiltonian for how they entangle with each other. And the rule is that they can entangle randomly. Basically, any pair of electrons can entangle with any other pair. It's not this very choreographed resonance in benzene. It's just totally random. So you take these 2 electrons, they can entangle, and they entangle while they hop from this pair of sites to that pair of sites. And then you can pick another pair, and then they can entangle. and so on. So all of these processes can happen. You can think of them as collisions. And these collisions don't come with a probability. They come with an amplitude. That's what quantum mechanics tells us. They come with a phase factor and a magnitude. And the phase factor is building in the quantum wave function, which has lots of phases in it. And these phase factors I cannot ignore. I have to account for the interference or the entanglement between successive interactions. I shouldn't use the word collisions because that implies you're talking about probabilities. All right, so all of these interactions can happen, and each of these interactions in a given, if I'm looking at a given system, would have a certain number associated with it, like transition amplitude. And so if you gave me a set of transition amplitude, so there's n electrons, there's n to the fourth possibilities for these processes. So you'd have to give me a set of n to the fourth numbers. And then I would take those numbers and figure out what the physical properties are. Now, in general, that's an impossible problem to solve. But what we showed was that if you just took those numbers to be random numbers, then the problem self-averages. And you can figure out the properties of such a state of matter. So this is, also like in Boltzmann theory, you don't need to know the position of every molecule. You just need certain statistical information, and you get a perfectly legitimate theory of a single piece of gas, single instance of a gas. Here also, if you take a single instant, if it's large enough, it will behave like any other instance. And therefore, you can statistically describe the quantum correlations. You can't use the Boltzmann equation, though. That's really the key. So here's, if you know a little bit of second quantization, an explicit representation of the Syk model. You have two electrons going from site gamma and delta to site alpha and beta. These come with this amplitude, u alpha, beta, gamma, delta. And the main assumption which allows solution, I won't describe the solution here, is that these numbers are statistically independent of each other. Okay, so if you solve this problem, you find indeed it has all the desired properties that we wanted in a strange metal. There are no quasi-particle excitations, and the typical relaxation time, if you perturb it, add a second extra electron or something, is h power over kT. So these are all things you can show analytically once you assume these numbers are statistically independent. Okay, so I'll just show you a little bit of actual numerical data. So here's, if you take this Hamiltonian and you actually determine the energy levels, there's an exponentially large number of levels. So if you have 100 electrons, there's 2 to the 100 levels, which is incredibly large. So this is just for, I think, 20 electrons or something like that. These are all the energy levels. And we're plotting, in fact, the density of states. So now you can ask, what is the density of states? Well, Boltzmann told us the density of state is the exponential of the entropy. So you have to go in and compute the entropy. And this is what we did in 2001. And you get this expression here. And the entropy has this feature that as you go to very low energies or very low temperatures, it remains extensive. So in a sense, it seems to be violating the third law of thermodynamics. The third law of thermodynamics is not a law, it's just an assertion. And in this particular system, this is violated in a certain definition where you send n to infinity first and then temperature to 0. Okay. Now, normally, if you have an exponentially large entropy at very, very low temperatures, this would tell you that you have a lot of electrons or a lot of states with exactly the same energy. They're highly degenerate. But if you zoom in here, there's no sign of such states. There's no degeneracy at all. The energy levels are all completely discrete and generic. And so if you look, so why is the entropy so large at 0 temperature? Well, it's because the energy level spacing, even at the bottom of the band, is exponentially small. These energy levels are really, really, really close to each other. And this exponentially small energy spacing tells you that, in fact, this is a system that does not have particles like excitations, because the number of particles is n, and there's no way you could take n particles and in a very small energy interval get e to the n states. They just can't form that many states at low energy. So that means that these are really highly entangled states, and if you go from one state to the other, they don't differ by adding and removing a particle as they would in a conventional Boltzmann quantum liquid. Here, each state is a completely different entangled state of all the electrons, which just happens to have energies that are close to each other. Of course, I'd like to say more than that, but that's really that's the key to the whole theory of strange metals, which are these chaotic entangled wave functions down to low energies. And the remarkable thing is that even though they all entangle in a complicated way, there's many properties that you can determine exactly. Yeah, so I've already said this. So where do these properties come from? Okay, I'm almost running out of time. If you actually look at the low energy theory, it turns out to be expressed in terms of a time reparamerization mode. And this, again, should ring some alarm bells, because Einstein theory of general relativity is all about the fluctuations of the curvature of space-time, which you can think of as space-time reparamerization mode. So it seems as if, there is a connection to gravity from the fact that you have this time reparamerization symmetry in the low energy theory of this black hole, of the Syk model. All right, so what is the connection to black holes? All right, so you can make a very specific connection to what are called charged black holes. If you take a black hole with a net charge, which probably there's hardly any of those out in our universe, and you solve Einstein's equation, you find a remarkable dimensionless transmutation. If you're very far from the horizon of a black hole, the space is 3 plus 1 dimensional. This is like our space-time. But as you get close to the black hole, the space-time factorizes. There's a curvature of space-time in a way that if you were coming into a black hole along the direction zeta, you would think that your world was one-dimensional. There's only one space and time. You would be totally unaware of the angular direction. So that's, to us theorists, that's a wonderful simplification, because you can try to do a quantum theory in one space and one time dimension. And that's a lot easier than doing a quantum theory of gravity in 3 space and 1 time dimension. So you have this dimensional reduction. But now let's assume, that, let's try to guess that if the Hawking answer applied, this would imply that the entropy of this black hole in 1 space and 1 time dimension with this ADS2 horizon should be the quantum mechanics of that one point, because when you have 1 space dimension, its boundary is 1 point. So is there a dimensional reduction? First of all, there's dimension of 3 plus 1 to 1 plus 1. And is there a quantum system at 1 point? Because you want the surface of that. So that will be a quantum system in 0 plus 1 dimension. Well, I've just given you a quantum system in 0 plus 1 dimension, and that's the Syk model. And it turns out you can show that you can start from Einstein's theory of gravity and end up with the low energy theory of a charged black hole, and that turns out to be exactly the theory of the Syk model. So there's a precise mapping between the Syk model and certain classes of black holes. And this also means that these discrete energy levels of the Syk models are an example of the discrete spectrum of a charged black hole. It won't be exactly the same spectrum because probably the black hole is not described by the Syk model. The string theory is something that actually gives you the exact spectrum. But the statistical properties of these levels here will be exactly the same as that of a charged black hole. Okay. And this is very different from what happens from string theory. In string theory, you actually do indeed get into these ADS2 black holes a degeneracy. But that's an artifact, I believe, of supersymmetry. But if you have a black hole with no low energy supersymmetry, as is the case in any black hole on a universe, then you will not get a density of states like this. You'll get a density of state that looks like this. Okay, all right. I think I'm out of time. I don't have any time to talk about this. So I've shown you the connection from the Syk model to a black hole. And for a certain class of black holes with a net charge and low temperature, the connection is actually extremely precise and has led to a lot of advances in our understanding of quantum properties of black holes. There's also a connection with the Syk model and the linearity resistivity. This is really current work in progress. I don't think I have any time to tell you about it. Let me just say one thing. You take a model of electrons in an ordinary metal, which occupy these states and don't occupy those states, and you couple it to some low energy boson by some coupling G. But to get the linearity resistivity, you have to take an idea from the Syk model. You have to allow this coupling to be random, not in some flavor space, but also in position space. And this is some recent work with my former student Avishkar Patel, my current student Hayo Go, and postdoc Ilya Astolitz that we just put on the web literally a few weeks ago. Okay, so to summarize, the main new thing I told you about is the Syk model. You may not like it, but you can't deny that it has some unique properties, and it's uniquely the model and models in its class, which are solvable despite having no particle-like excitation. So having one such model is always great because it teaches you a lot. And to a surprise, we found, or maybe not surprised, because we're learning some fundamental principles, that once you lose quasi-particles, you get a number of other properties. One of them being this Planckian time thermalization, and no dependence on the thermalization time on microscopic energy scales. And then furthermore, at least in the Syk model, this may not be very general. You find this time renormalization symmetry, which then connects to quantum gravity in one space and one time dimension. And this has led to some progress anyway in understanding some of and resolving some of Hawking's paradoxes in certain simpler situations. In particular, understanding how the entropy of a black hole evolves as it evaporates. This is not something I've said anything about or anything that I've personally worked on. And in very recent work, we are excited. We think we have a possible mechanism for the universality of this linear T resistivity. Okay, thank you very much.
Well, thank you very much, Professor Sachdev, for that very fascinating talk. I mean, it really is mind-boggling that in some sense you can view a black hole as a kind of holographic quantum state. I can't even wrap my mind about what that means, but I will now.
I can barely, it's a process of slowly understanding, but that is, I think, one of the amazing new ideas in this idea of holography in modern physics. Yeah.
So I will now, without much ado and without wasting time, and ask my colleague Professor Navinder Singh to carry out the question and answer session. I'm sure there'll be a lot of questions from the audience. Navinder.
Thanks, Jerry. Thank you, Professor Sachdev, for this wonderful colloquium, Vyakhyaan. So now the stage is open for questions. So first of all, I would like to ask my colleagues in this WebEx platform, so they can ask questions directly. And after that, I will read out questions in the chat box if there are any in the chat box. Please go ahead. So there is a hand raised by HM Hirmaya. Please, HM. Yeah, you have to unmute yourself. HM, you have to unmute yourself.
Okay, am I audible now? Yeah, okay.
Yes.
Professor Sachdev, it was a fantastic colloquium, and thank you for this talk. And I have two questions. You introduced the concept of a limiting case for the relaxation time, which was essentially 1 by temperature in H cross KB.
Yes.
Does chemical potential or the density is not a relevant scale there? I mean, does that come into picture for relaxation?
Yeah, that's a good question. So, first of all, I should emphasize that there's no proof, but there's a claim that as temperature goes to zero, and this is in the limit as temperature goes to zero, in any quantum system, you cannot find a relaxation faster than h bar over kT. Okay, so that's a very big claim. I mean, it's a very broad claim that has never been proven. But I'm
1 by
not
mu
aware
is not
of
a
any.
relevant scale. I mean, 1 by mu is
Sorry,
not
1 by
1 by mu meaning the chemical potential of the electrons or
well,
hormones.
I mean, that certainly is a time scale, but I don't believe it's bounded by that. So the question is, yeah, I mean, as temperature goes to zero, the thermalization time has to diverge. You can't. So once there's kind of a speed limit, you cannot equilibrate faster than that. There's no such limit in classical mechanics. Classical mechanics, h bar goes to zero, so the lower bound is zero. So you can always saturate as fast as you can. Yeah. So that's a conjecture. Okay. I think I probably was the first to make this conjecture in the preface of my book in 1999. And so far, there's no counterexamples. But there are many examples of systems that saturate this. That is, if you take a Fermi liquid, it obviously obeys it, because in a Fermi liquid, the time goes as 1 over temperature squared, and that's always bigger than 1 over temperature. Okay, so Fermi liquid, the thermalization time is 1 over temperature squared. That's just what comes out of the quantum Boltzmann equation. So for a Fermi liquid, it's obeyed. The bound is obeyed. So you want to make the bound, you want to find a system that will relax faster and faster, much faster than a Fermi liquid. So the Syk model is one that reaches the speed limit. It reaches the speed limit. It relaxes as fast as h bar over kT. Now, we'd like to find, maybe there's some model out there that will relax even faster. But I believe there is no such model. If you come up with one, I would like to know about it.
Okay, the second point is that you kind of estimated this resistivity, I mean, for the system of the Syk model.
Yeah.
T.
That was very, very quick. I had no way to describe that.
Yeah. But have you looked into any other transport property, like, for example, eta over S? Does it?
Yes. So I've written some papers with Avishkar Patel on that a few years ago. And that certainly does also obey the Compton-Sohn-Starines bound, which is 1 over 4 pi. It's actually much bigger than that in a non-Fermi liquid. Yeah, and there have been others also. We haven't looked at thermal transport yet in our most recent model, but yeah.
Or diffusion.
Yeah, so these are all things in progress. So we've just okay.
It's a very interesting model. So I was thinking.
Yeah, this is not the Syk model. I had no time to just, the Syk model is a toy model. That it's really just, we never thought it was worth anything, but initially anyway. But after a while, the fact that it's literally a model of a black hole is kind of amazing. I don't think it's literally a model of a strange metal, but it taught us a lot. And there's a lot of inspiration one can take from it, which is leading to some recent work that I didn't have any time to go into, but I just sketched. I just flashed it at the very end. Yeah.
Thanks, HM. So next question is by RP Singh. RP Singh, please unmute yourself.
Yeah, thank you, Professor Sachdeva, for a nice talk. I wanted to know about this. You talked about charged black hole. So how one
Yes.
can see the signature of charged black hole, and suppose one can see the signature of charged black hole, whether one can connect then gravity and quantum entanglement or space-time curvature with quantum entanglement, which is like very burning question, how to connect like entanglement and with gravity.
Yeah, so let me share my screen again. Yeah. Okay, so this is a picture of a black hole which happens to have a certain charge. Now, of course, the problem is if you have an astrophysical object with a certain charge, it will attract, if it has positive charge, it will attract negative charges from the rest of the universe, and they will come in and neutralize the whole thing. So probably there's no such thing in our universe. But
But if you take the black hole as a topological structure, you can have positive and negative topological charge, and they can come together and annihilate. If you take them as a topological structure, if you see the image of a black hole, they have recorded, it's very similar to one of the vertices, and if you take them as a topological structure,
I'm
positive
here.
and negative.
Yeah,
so they can annihilate, yeah.
Okay, then. Okay, there may be some topological charges that are stable that way, yes, possibly. But I'm just looking at Einstein-Maxwell theory, period. So I'm just describing electromagnetism. When I meant charge, I meant an electromagnetic charge, which obeys Maxwell's equations. So as we know, the protons are positively charged and electrons negatively charged. So you would have to have more protons and electrons in this astrophysical object, which is highly, highly unlikely. So there is, but if you just had a universe where there were more positive charge than negative charge, then such an object could form. And so you can solve the Einstein-Maxwell theory. And when you solve the theory, you find this kind of remarkable transmutation that if you were falling into the black hole out here, you would think the space was three-dimensional. And as you got closer and closer to the black hole, falling this way, this direction, zeta is the same as this direction, you would start to think that the world is one-dimensional. So this is a feature of Einstein's equations. And it's surely correct. It's just to do an experiment on something like this would be very hard. And what I was using was so as you're falling and the world becomes one-dimensional, then if you apply quantum mechanics, that tells you holographically the world is zero-dimensional. And what is that physics of the zero dimensions? Well, it's the Syk model. So that's where the charged black hole, amazingly, turns out to be very, very closely connected to the Syk model. I certainly didn't know of the existence of such black holes when I came up with the Syk model, but in about 2010, I made this connection before anybody else, actually. Yeah. Okay. Thank you.
Any proposal to see these kind of black holes? Any proposal from any quarter you can recognize these black holes by?
Well, I mean, if you have a charged black hole, you would see negative charges falling into it and giving off radiations. I mean, you would know immediately that it was charged.
Oh,
yeah.
Thank you.
So next question is by Namit.
Sachdev, for an interesting talk. I was just wondering, since there is some connection between Syk and black holes, suppose one computes something like OTOCs in both the backgrounds for both the systems.
Yeah.
Does one expect something similar to appear? Meaning, in the sense that will OTOCs will also fall under quote unquote a universality class for these two systems?
Yeah, absolutely. In fact, that was another motivation which I didn't discuss. I didn't go into OTOCs, which are out of time order correlation functions. And there was a amazing paper by Steve Schenker and Douglas Stanford, who first computed the OTOC in Einstein gravity for a generic black hole. You could also do it in charged black holes. They did it for a Schwarzschild solution. And they gave very general reasons that the OTOC should have a Lyapunov time, which is exactly 2 pi kT over h bar. And that's what you get out of, basically, solve Einstein's equation, you put in the Hawking temperature, and you find the O torque is 2 pi kT over h bar. And then later on, Kitaev, and that's how it became the Syk model. Kitaev showed that what's now called the Syk model has exactly the same time, 2 pi kT over h bar. So I just mentioned the thermalization time, where I said it's of order h bar over kT, which is what I was thinking about before I knew about OTOCs, and made the connection to black holes. And now that same connection is much more precise, because even the factor of 2 pi is the same. And that was not shown by me, that factor of 2 pi was being the same was shown by Kitaev and Schenker and Stanford and others. Yeah.
Thanks. Thanks.
Okay, so I see that there is no hand raised in this WebEx platform. So maybe I can ask one question, Professor Sachdev. So my question is related to the resistivity from the Boltzmann equation, 1 by t square. So my question is, for a single band electron scattering conserve momentum. So is a two subsystem of electrons assumed when the Boltzmann equation is applied? Or
yeah, so some impurities, yes. Yeah, absolutely. I mean, I was simplifying for a colloquium, but you're of course absolutely right, and that's a very, very important issue. And it's one of the major stumbling blocks for coming up with the theory of a strange metal. So in fact, that's what our recent work is all about, is how do you understand a strange metal while accounting for conservation of momentum? That's really the key question, so which you're raising. What did I do with my slides?
No.
Sorry.
Yeah, so when we do this classical...
You're seeing my... let me see. Yeah, so I want to just show this slide.
Sure.
Yeah, here we go. Okay, now you can see the right slides. Okay, so I just mentioned, yeah. So if you do a theory of just electron interaction in a translationally invariant metal, that doesn't give you any resistivity. In fact, you need Umklapp scattering or some impurities. So if you have some small number of impurities, then you will get a t-squared resistivity in the Boltzmann equation as a correction to the residual resistivity. So you face the same issue in the theory of a strange metal. If you take a metal, a Fermi surface coupled to bosons by some Yukawa coupling, which could also, like this one, then you can get a strange metal in the sense that there are no quasi-particles, but the resistivity of this metal is 0. It's just strictly 0. It's almost like a superconductor. That hasn't stopped many papers being written on this model and saying it has some t to the 4/3 resistivity, which you may be familiar with. The t to the 4/3 law is just simply wrong. So we started, first of all, you can make this random in flavored space, but that still has 0 resistivity for precisely the reason you mentioned. But to get the linear to resistivity, our claim is you have to take this coupling and make it a random function of position. So you have to put in not just random impurities, you have to put in random interactions. And that's the claim in a very recent paper. Okay, I don't know if it's right, but it is certainly true that it seems to give results that are very appealing, that you definitely do get exactly linear resistivity and so on. So that's, very recent work we are very excited about, but we'll see where it goes. Yeah.
Thank you. So my second question is related to the Moria with the SCR theory, the self-consistent renormalization theory, the Japanese group.
Yeah.
They applied the SCR theory to calculate the resistivity by using expressing the resistivity in terms of the dynamical susceptibilities computed from their SCR theory, and they get T-linear resistivity. So what is your comment on their work?
Yeah, I think there's a similar problem there, which I have written papers on that, in fact. The resistance of that theory is 0, actually, because the T-linear resistivity is coming from very close to the hotspots. And very close to the hotspots on the Fermi surface, you can see there's a conserved momentum which they just ignore. So I don't think that theory is right. Yeah.
Okay. Thank you very much. So now So is there any other question from the people who have joined on this WebEx platform? Please raise hand or directly ask your question. Otherwise, I will read questions from the YouTube. Okay, so let me read questions from the YouTube. So there is a question by Dr. Surindra Simpokarana. So his question is, any mechanism has been guessed to explain quantum entanglement like Bohm potential or vector potential or Arnott-Bohm effect, etc. Then he says here whether classical hologram concept will be involved or quantum hologram, question mark.
Okay, there's a couple of questions there. So one is about the Arnott-Bohm effect. The Arnott-Bohm effect, of course, is a very it's a key effect in quantum mechanics, where if a particle moves around a magnetic flux tube, it picks up a certain phase factor. So that by itself is a single particle effect. It's not anything to do with entanglement. But in certain entangled states, like the fractional quantum Hall states, it turns out there's something very analogous to this, where because of the entanglement, as one particle moves around another particle, it sees a flux. So it picks up a phase factor, and you have what are called anyonic statistics. So there you have an entanglement leading to Arnott-Bohm effect, which leads to the existence of anyons. So there is a connection, but it's not. In my case, the Syk model, these coupling constants had a random phase factor. So that was the Arnott-Bohm phase factor, but I just took it to be completely random. That's what we did. Okay, and the second question was about holography. Yeah, so classical holography, the word holography comes from where you take an image of a three-dimensional object and you make an image which is two-dimensional, but that image is made in a clever way that you preserve all the three-dimensional information and you can reproduce the three-dimensional object, at least all information about the 3D object in 2 dimensions. So that's the word holography, that's what it means. And that's effectively what happens here too in the quantums in a black hole. You have all the information about the black hole, meaning its entire wave function, which is in 3 dimensions. And all of that information, we believe, is encoded in a hologram, which is a bunch of qubits or string theory or whatever, or conformal field theory or something like that. There are many possible options, but the hologram, the quantum description is in 2 dimensions, not in 3. And that's why the word holography is used. But beyond that, of course, the actual mechanism, the way you make a laser hologram has nothing to do with the way you make a quantum hologram. That's just fully quantum mechanical. Yeah. Just the same word is used.
Okay, thank you. So the next question is by Paramita. So she asks us, thanks a lot for the excellent talk. So he has 2 questions. So one is it only copper oxide? I guess she means copper oxide, copper cuprate superconductors, which is found to show strange metallic state till now, or is there any other example? This is question number 1.
Sure, absolutely. Let me answer that. The iron-based superconductors of pnictides also show strange metal behavior. I showed you twisted bilayer graphene. They also show it, and there are many other materials. It's really very common, and in fact, it seems to be essentially universal behavior. Any system that is quasi 2-dimensional. It seems.
Yes,
that's where it seems to be most likely. Yeah.
So her question is connected with the first one. So she says, if already found in other materials, does the phase diagram always come with superconductivity?
A great question. There may be a few exceptions, like strontium root, but where the TC is very low. But yes, it seems to be correlated with relatively high temperature superconductivity. Yeah. And that's really one of the reasons for the fascination with the strange metal, because it seems, that's where the mystery is. Once you understand the strange metal, you will hopefully be on your way to understanding higher temperature superconductivity.
Okay, thank you. So the next question is by Akriti. So she asks how one can quantify quantum entanglement in strange metal like situations. What is the entanglement monotone or non-monotone in your study?
Well, okay. That's a good question. I mean, people are coming up with all kinds of measurements of entanglement in many body systems. I am not a specialist on that myself, but the most common is the entanglement entropy, which theoretically is a very useful thing, but it's almost impossible to measure in a big system. But it's a powerful theoretical tool for characterizing strange metals. What was I going to say? Yeah, and in terms of monotone, yeah. So the entanglement entropy obeys something called subadditivity, which is basically somehow saying that any qubit can only be entangled with one other qubit at a given time, roughly speaking. And so there are general inequalities that the entanglement entropy obeys, which can also be very useful for testing consistencies of theories. And in fact, it's been very crucial in trying to understand radiation from a black hole. The whole Hawking paradox is entirely connected to the subadditivity of entanglement entropy.
Okay. So, okay, if there is no other question from the audience, so I request my colleague Vineet for the vote of thanks and conclude the session. Vineet, please. Hello, Vineet.
Unmuting is to unmute.
I'm audible now.
Yeah, you're audible. Yes.
Yeah, thank you very much, Professor Navinder Singh. That brings us to the conclusion of the 35th episode of PRL का अमृत व्याख्यान. I would like to first thank Professor Subir Sachdev for accepting our invitation and giving an excellent talk on the quantum entanglement at PRL का अमृत व्याख्यान. Also, we are thankful to Professor Sachdev for answering the audience's questions after the talk. Second, I would like to take this opportunity to thank our audiences on both the YouTube and WebEx platforms. Next, I express my sincere thanks to PRL Director, Professor Anil Bhardwaj, Dean PRL, Professor D. Pallam Raju, and Chair, Professor Nandita Srivastav, and Co-Chair, Professor Lokesh Sahu of the PRL का अमृत व्याख्यान Committee for all their support to organize this व्याख्यान successfully. I also thank my colleagues in the Vyakhyaan organizing committee for successfully conducting this episode of the PRL का अमृत व्याख्यान. I would like to thank Professor Navinder Singh for conducting the question and answer session and Dr. Manesh Samal for posting the questions from the YouTube. I sincerely thank you all for being part of the Azadi Ka Amrit Mahotsav and celebrations for PRL at 75 years. Kindly visit our website and other media platforms to know more about the upcoming events being held at PRL, in particular PRL का अमृत व्याख्यान. With these words, I propose the closure of today's episode of the PRL का अमृत व्याख्यान. Thank you very much.
Thank you. Thank you very much.
Thank you.